Recently, one of my colleagues sent me some pictures of a condominium high-rise building, and he took these pictures in the parking garage below the building. These are pictures of these strange rusted metal dots that are on the slab next to a column. And so he texted me these pictures and called and said he had two questions. One was, what are these things? And two, is this a serious problem or a minor problem? So before we go on into the video, I want you to go into the comment section and tell me, without knowing anything else, whether you think that this is a serious problem or probably just a minor problem. And by the end of this video, I'll answer your question. All right, so today what we're going to be talking about is stud rails. These are a technology or a material, I should say, that we use in order to strengthen concrete slab and beam connections. And so in order to understand, why these are necessary and what they do, we're going to kind of look at the different types of common slab construction. So here we have three types of reinforced concrete slab construction. On the far right, you can see that we have a beam slab floor. And what this means is that essentially you have columns, and then on top of the columns are beams, and then on top of the beams is a slab. Now, typically this is a three-step construction then for every floor. You've got to form and pour the columns, you've got to form and pour the beams, then you've got to form and pour the slabs. Sometimes you can pour the slabs with the beams at the same time. But you can see there's typically this extra, if it's not an extra pour step, it's at least extra work that has to be done. In the middle, we have what's called the flat slab floor, but really what I'm most interested in is the fact that we construct these typically with a capitals or drop panels or both. You can see those at the very top of the columns, and the whole purpose of that is to sort of spread out and distribute the load. And you can kind of think of it as like if you're a waiter or a waitress and you're carrying a tray, you're going to spread your fingers out as much as possible in order to try to distribute the load across that tray to make it more balanced and easier to carry. That's sort of the idea here. But what realtors and developers really want is they want what's on the left, which is called the flat plate slab construction. And in this case, we have no beams, we have no capitals, and we have no drop panels. And the reason why they want this is because, one, it's faster to construct, two, it's cheaper to construct, and three, it provides more sellable real estate, and it provides better views because there's no beams and columns and capitals that you have to frame around, which could possibly block your views of, let's say, a beachfront or something like that. So this is what most contractors and developers want to build these days, particularly in Florida, but around the world when we're dealing with reinforced concrete structures. This is the most popular by far. And so in order to understand why this is problematic, though, is you have to understand how punching shear works. If you've been a fan of this channel, you know we've covered punching shear on previous videos. And so what you essentially have is you have weight that is on the slab. This is like a cross section, if you will, like a cut through an apple. And you have this weight on the slab, whether this is people, filing cabinets, vehicles, whatever's on the slab, you have this load pushing down on the slab. And then the earth pushes back to resist this load, right? For every action, there's an equal and opposite reaction. So the earth pushes back against this through the column. So the column is essentially exerting a static force in the opposite direction. And so just like a pair of scissors where you have two pieces of metal passing by each other, you essentially have the potential to shear the connection between the slab and the column. And so you would expect it that you could break like this. Okay, and then therefore you would have this force passing this way and you would have this force passing that way, and this creates that shear action causing it to break around the column. The only caveat to that is that because of the forces that are involved in the slab itself, there's these things called flexure and bending moments and things like that, and the slab actually wants to sort of deflect down, if you will, like this. It's very subtle. You can't usually see it with the human eye, but because it wants to flex down like this, you actually have an extra combination of forces happening here. And so therefore, instead of the shear being perfectly vertical like I drew it, the shear crack actually looks something like this. And this is what we refer to as our shear head or our shear head plane. I want to show you what this looks like from the top view. So over here on the right, we have what I just drew, which is the shear head plane on the column to slab connection. And then on the left side of this screen right now, we have the top view. And the top view sort of shows the column. and it shows the perimeter of the shear head. And so in order to get this slab to punch and fail and fall down around the column, you need to break the entire shear head. So what you're really dealing with is you're dealing with the area of the shear head, which is, I'll shade it right here. And so this is the area of concrete that is resisting this punching shear. It's resisting this break from occurring, and you can see that we get that shape from these diagonals that I drew over here on the right. All right, and as an actual real-world example of this, you can see at Piper's Row Car Park in the UK, and you can actually see that exact shear head in an actual failure, showing that shape at the top of the column. It's not perfect. The world never is exactly perfect, but you can kind of see this general idea that this doesn't just punch up straight through. Now, if you've been following this channel and you know about Champlain Tower South, and you remember that those columns ended up shearing and the tops of them looked sort of like this, and the slab used to be here, you can see that doesn't look anything like a normal shear head. That's actually part of the interest of the investigation in Champlain Tower South, is why didn't they fail in a typical expected pattern? And there's a lot of people, myself included, that believe that the reason for that shape is because the top of the slab was severely damaged due to corrosion and aging, and because this was in such a deleterious condition, it created an odd punching shear profile. So what our goal would be in order to strengthen this slab to column connection is we can't really increase the thickness of the slab. That's sort of maybe a fixed factor in our design, and we can't really increase the size of the column. So if those are two fixed things, the only thing we can hope to do is to take that shear head shape and maybe try to make it bigger. Let's spread that out. Why do we benefit from doing that? Well, if you remember, I drew you this area here, and this is sort of our shear plane for a normal shear head. Okay, and so what we're going to do is, if we can spread this out, then we can essentially create a shear head that's more like this size, and you would obviously have a much bigger area to work with, which means that you can resist more punch through. One of the recent, and I say recent as far as construction history, one of the more recent inventions is the invention of the stud rail. Now, this is what they look like. They come in various sizes and shapes, but it's basically a three-piece component. It has a steel shaft. It has the steel rail that the shafts are welded to, and then they have the head. And the head and the rail provide anchorage, which I'll explain a little later. And then the shaft itself provides the ability to transfer the forces, and we're going to show you how all that works in a second. Some real-world photos, though, of these being installed. You can see on this job site they have installed lots of shear rails, and I'm going to kind of circle where they're at. I'm sorry, stud rails in the shear head plane. Okay, so this is called a cross pattern. So they put them in here as a cross pattern, tons of these things. Okay, and the idea is to strengthen that connection between the column and the slab and to spread and make that shear plane head bigger. You can also, though, as opposed to the cross layout, you can also do a radial layout. One of the other interesting things you'll notice about this radial layout diagram is that the stud rails are actually installed upside down, because the heads are here at the bottom, right? And you'll find that it doesn't really matter whether you install them right side up or upside down. They're still going to provide the same functionality. And here's a photo from a job site where somebody is actually installing them upside down. This gives them some freedom to go ahead and lay the other reinforcement without having these stud rails in the way. And then you can sort of get these stud rails to fit in where you need to fit in by installing them upside down in this manner. Okay, so when we go back to our cross-section, slice through the apple type view through this slab and column connection, and we draw in those stud rails, we can start to see how those stud rails may work. Again, the goal being to take our shear plane from here, or our shear head size from there, and try to make it out to here. And that's the goal that we're going to try to accomplish. But how does that work? Well, we're going to zoom in and we're going to show you that. Let's say that plane comes across like this. And that's your shear head plane if the stud rails weren't there. Now, in order for the slab to fail, you're going to have the slab essentially moving down and the column staying put. So you would end up with a slab that's sort of down here like this, right? So in order to pull this area, this slab down away from the shear head, you would have to pull against these stud rails, okay? And the stud rails don't want to pull out because they have the stud heads, and the stud heads provide what we call anchorage. And what that means is that if you're going to be, if this portion of slab wants to go down, right, and you're going to then exert a force on the steel stud rails that wants to pull it down, then it has to pull it out of the concrete, which is staying. This is in the way we're analyzing this. This area is going to stay. The rest is going to fall, right, in a collapse scenario. So what we're doing is we're sort of predicting the way something's going to collapse, and we're going to try to resist that. Now, let's focus on this pulling action here on the stud rails, and let's talk about how this all works. The stud rails are then embedded into the area of the concrete that's going to stay, and the reason why they have those heads and why those heads are so important is because they provide that anchorage. And what that anchorage does is it essentially distributes the load into the surrounding concrete. Okay? And so what you have to imagine is like if you're at the beach, okay, and you stick a pole deep into the sand, it's pretty easy to pull that pole out. But let's say you dug a hole and stuck your foot in the sand and then buried your foot. It can be very difficult to pull your foot out because your foot actually creates a sort of anchorage, and you have to lift a lot of soil in order to get that foot out of the sand. That's exactly what this anchorage is doing. And now that you kind of understand what the anchorage is doing with the stud rails, hopefully you can realize that if you flipped the stud rail upside down, it's going to provide that same level of resistant force, anchorage, if you will, that we need in order to stitch this together. That's going to be the key word that I want you guys to remember. That essentially what the stud rails are doing, I'm going to clean this up real quick. Essentially what the stud rails are doing is they are stitching, just like you would stitch anything else, or sewing, if you want to use that as an analogy. They're essentially stitching this wound together before the wound ever appears. And so therefore, if you're stitching this together and you have an adequate amount of stud rails and you're not going to crack along this area, then what you're going to do is you're going to shift the crack shear head plane. Maybe you shift it over here, okay? Because it's got to move out somewhere. It can't. This one isn't going to work. That's not going to crack because you've stitched it together with the stud rails. So then it shifts over to this location. But you can see this location is also crossing stud rails. And you got stud rail crossing here, and you got this head that's kind of in there, right? So it's stitching it together, so that doesn't work. So ultimately, the shear head plane now kind of moves out to here. And if you remember what we talked about before, we can't control the thickness of the slab, we can't control the size of the column, but what we can do is try to grow our shear head plane in order to resist, or in order to provide extra connection strength between the slab and columns. So you can also kind of think of it as building a column capital or a panel, but you're building it inside the slab, which is a really interesting way to kind of think of it. So if you look over here on the right side of your screen, you'll notice that I have two cross sections. One says no stud rails, one says with stud rails. So just reiterating, the one with no stud rails would fail in this manner. It would have that kind of shear head plane going on. And the one with stud rails would shear in this manner. Now, if you come over here to the left and you look at the top view, you'll see that they provide two different shear heads. So the one with no stud rails is this area. And remember, the area is what, we're not going to do any formulas today, right, or anything, but the area is what provides the resistance, the amount of shear area we can create. And so this is not exactly 100% accurate, but it's accurate enough for this video purpose. And so what you have here is you have the shear area that I have highlighted, or I should say I have hatched in turquoise. And then and that covers the area with no stud rails. The area with stud rails is out here, and you can see that this area is much larger, and you can actually observe that it takes me a lot longer to hatch this area in. But just visually, if you compare the two to each other, it should become very apparent and obvious that the red area as far as area is concerned, not as far as size or perimeter or anything like that, but as far as the area is concerned, it's a much bigger area than the no stud rails area, therefore accomplishing our design goal. Now, let's get back to the pictures I showed you at the beginning of the video, this actual project that one of my guys was on and took these pictures of. Now you're beginning to understand, okay, what I'm looking at now, I believe, are the heads of stud rails. You can see on the picture on the right that they're very round and they're spaced very evenly between them, between one to the other. So to me, this looks very much like a stud rail. We went ahead and got the drawings from the client. We looked at the drawings and found that indeed the engineer who designed the building did include stud rails in the building. Interestingly enough, though, he also included a note that said that, these stud rails should be adjusted as needed by the contractor in order to achieve the proper concrete coverage. So what they ended up with was this cross-section. And again, we're looking at a cross-section view. They ended up with this where the stud rails are up at the surface of the concrete. And what the engineer was saying was that if you're going to have this situation, because he did specify the size and height and everything of the stud rails, but he's saying if you're going to have this situation in the slab where you need to slope the slab, and that actually is the problem here on this project, if you're going to slope the slab and you're going to possibly end up running into these stud rails, that the contractor needs to spec or needs to order and use shorter stud rails, but he didn't do that. And so the idea behind the engineer was that there would always be some amount of concrete cover over the stud rails to protect them from corrosion, which is sort of what's going on here in this other picture. So not only are the stud rails have barely any coverage, pretty much like no coverage in some locations, but now they're beginning to corrode. And so zooming in on here, the question that I said I was going to answer, the question really that the client and my colleague had for me was, is this a serious problem or is this a minor problem? As it sits right now, it is my opinion, based on those pictures and based on our site visits that we've done, that it is currently a minor problem, but it needs addressed. So minor problem is the answer, and here's why. If you remember when we talked about how stud rails work, the key was the anchorage. You're going to stitch the wound together, right? You're going to stitch together that crack, that shear head plane. And if you're going to stitch it together, because we're dealing with such short stitches and we're dealing with concrete that's maybe only 6 or 8 inches thick, then you have to have this sort of anchorage head. You have to have the head that has the ability to distribute the load to a wider area in order to achieve that stitching capacity. Now, I believe looking at the photos of this particular client's property, those heads are still doing this. They're still exerting a force on the surrounding concrete. However, if they are allowed to continue to corrode, what they will end up doing is they will end up spalling the concrete around the heads to such an extent that, and spalling again is breaking apart of the concrete due to this internal expansive force. So the stud rail head would rust, and that rust would expand and blow apart the concrete. So if these are allowed to continue to rust and deteriorate, and you start deteriorating the concrete around, there's not really much patching that you're going to be able to do in order to reconstitute their ability to distribute the force. Because how is that stud rail head going to distribute a force when all of this concrete is actually broken apart around it? So currently, minor issue, but it definitely needs addressed and corrected. So tell me, were you right or were you wrong? If you like this channel and learning about everyday applications of engineering, or you're just a lifelong learner like me, you'll love Brilliant, the sponsor of this video. Brilliant is a website and app that utilizes interactive, hands-on learning to sharpen your mind and learn new STEM skills that you can actually use in everyday situations, from solving real problems you'll face to just impressing your friends at your next dinner party. My favorite topics on Brilliant include engineering and math, obviously, but also foundational logic, which you can use to enhance your reasoning skills using puzzles and riddles. I mean, who doesn't want to be the next Sherlock Holmes? As we age, we need to keep our minds sharp and our brains agile. Brilliant is a fun way to accomplish these goals by developing new neural pathways with real results. And you can do this at your own pace and on the go. Viewers of this channel can sign up now at brilliant.org/building integrity, and the first 200 of you will get 20% off of your annual premium subscription. I want to thank Brilliant for sponsoring this video, and I want to thank all of you for supporting this channel. Thanks.